Hi, so we recently did some stuff on lead, and before that I did a video on handling lead as kind of a precursor. It's called The Dangers of Lead if you want to look it up. And we're going to do some stuff where we plug some scary electronics straight into the wall, and I thought it might be an idea to do something on the dangers of electricity and how to look after yourself when you're dealing with it, because some of those things might, some of the things that we're going to do might shock folk and get folks saying, hey, that's dangerous. To a degree it is. But it's handy to know this stuff, I think. Now, the information isn't going to be terribly complex. It's just going to be an introduction, a basic what is, some stuff that you need to do to look after yourself. So if you don't feel like listening to that, then by all means skip ahead. But if you do look at the other videos and post the health and safety advice, I am just going to point you at this video. So it's up to you. Now then, electricity people like to think of as some scary, dangerous beast that leaks out of the wall somehow and is going to get you if you're not looking out. But it's actually one of those things that we have in fact tamed tremendously. And every time you make a drink or use a kettle, you come into very close contact with it because you've got this thing. This thing is just a kettle lead and it plugs straight into the wall, and out of the end are the wires that go into every single appliance you ever use. So when you touch that, you're extremely close to 230 or 110 volts. But of course, I can do that all day long and nothing's going to happen to me. The electricity is not going to get out of there and grab me. It's perfectly safe to do that. The only bit that isn't safe, as we get to it, is that bit. That bit is bare copper and it's the conductor. If that was plugged in and I were to touch that and that while wearing a chainmail suit and standing in a pool of water, I'm going to fry and die. Absolutely, okay? But if I do that, nothing's going to happen to me. I have to touch that bit. So the very basic safety advice concerning electricity is whatever you do, don't touch that. So how can you be more simple and straightforward in your health and safety advice? Do the very best you can not to touch that. In fact, do everything you can not to touch that. Touching this bit, it's going to do nothing to you. Touching that bit is going to kill you. So when you're dealing with electricity, don't touch the bare conductors. Don't try to put those on your tongue or you'll be very sorry. If you pull lots of things apart, which obviously I do pull lots of things apart, you might imagine that in all of that equipment that you use every day, toasters, kettles, your oven, then there would be some superb safety features in there to stop you killing yourself. When you pull things apart, what you actually find is there isn't. There's hardly anything in there to protect yourself. An example of that is this. This is an ordinary light. Now it's called a Baton fitting, and you fit it onto a piece of wood, and if you unscrew it and have a look inside of there, all you will see is those bare ends screwed into a terminal. There it is. That's a brass terminal with a little plastic cap to stop you touching those bare ends. Under that plastic cap is a bit of brass like this that bare wire screws in. There is no safety feature, in inverted commas, on that. The safety features are actually in the installation, they're in the consumer unit. But here, there's just absolutely nothing. That red wire and that blue wire goes straight to the filament in here. If I undo that and you have a look down there, those two prongs, that one and that one, they're connected directly to the mains. So why is it every time we turn a light switch on, we don't blow ourselves up? Because there's no protection in this. There's no way to stop you blowing yourself up, you would think. So why is it that we don't blow ourselves up? Well, the main reason actually is contained in here. This is in fact a resistor. It's just a resistor where one end is connected to the live wire, the other end is connected to the neutral wire, and when the electricity flows between those two wires, which it does because it's just connected just like that, then that resistor holds back the flow. It's actually often called a current limiting resistor because only so much can flow through there. Now you have one way of thinking of electricity, and a really good way of thinking of electricity, is thinking of it as a flow of water. and the wires as being pipes. If I have a lot of water in a very big pipe, I'm going to get a massive amount of flow. If I have a little water and a little pipe, then not much is going to flow. And that's what resistors do. Resistors are kind of like pipes of varying diameter. Now the amount of water, if you like, that we have is fixed by our supply. The push of that water is the voltage. Here in England it's 230 volts. That's how much we're pushing through. And we're always pushing that amount through when it comes to a household supply. That resistor in here is a fixed pipe diameter, and they work out what that pipe diameter is to get a certain amount to flow through there. So this actually limits itself. It draws as much current as it needs. It can't draw any more because of the pipe diameter. And that's worked out for that, which is why it's safe to put it directly across those two. And that's a very common thing. That kind of resistor directly across the wires is what you see an awful lot. Now this is a heating element that I took from a cooker. And it's very similar. It's got a metal rod, and in that metal rod you can see the white ceramic here is packed a lot of ceramic, magnesium oxide I think it usually is. And then in there is a resistance wire that's actually very similar to the stuff that's in the light bulb. That's why you see these glow red when they get really hot. And these are connected directly to that wire, one live, one neutral, and that plugs straight into your wall. And that will actually limit the amount of current that's drawn because of the size of the pipe. If I put that voltage up, it'll draw more current because it's got more push. If I put that voltage down, it'll draw less because there's less push, but the pipe diameter remains the same. If I change that pipe diameter, that is, I get a wire of lower resistance, then more current will flow. It will draw more current. And that's only because the pipe diameter is bigger. So it's quite safe to put these things directly across these two wires because they limit themselves. Now that's quite an interesting concept really of self-limitation, because obviously another way of protecting yourself from drawing too much current and blowing everything else is to put something in to limit it. Now it can be limited all by itself just because of the way it's built, just like the lamp and the heating element are limited all by themselves. Or you can put that in with the thing that you do. So say you're going to do something scary dangerous like we did with the capacitor. All we actually did was put a light in line with it because that will limit the current, as it must do because it was made to do that, because that pipe diameter is the size that only so much can go through at that push. So we can put that in as a safety factor. Now, it's a curious thing, but we don't use electricity for that much. We think we do, but we don't. We use it to heat stuff, to light things, to move things, and to communicate. So we have heat, light, movement, signals. That's all we actually do with electricity. Here's the inside of a motor. In there we have a couple of wires coming out, and it's just one big coil. Lots of these things are coils, incidentally. It coils all the way around. Actually, it's 3 in this case, but that's only for the purist. It coils all the way around. When we connect that up, and it's quite safe to connect that up straight away, one to there, one to there, it will draw a certain amount of current fixed by the pipe diameter and the length of the pipe, that is the resistance, and it will create a magnetic field in these little iron bits, and it will make that move if we put it in a magnet. That's what a motor is. So all of this stuff, motors, lights and heaters, are connected directly to the mains the minute you plug them in. It's quite a common feature. And in themselves, they don't have much in the way of safety in an awful lot of this stuff that is limited beyond stopping you touching them. You'll find that these end wires actually are very often clamped down tightly. They're in an extra little plastic box. They have a brass clip on them with a plastic clip, with another plastic clip, big plastic case. You can't get to them, and that's the safety feature, because that's all the safety feature you need, because electricity, as long as it's in that wire, isn't going to do anything to you. You have to touch that bit for it to do something to you. and what it'll do at that voltage is kill you, but you have to touch it. So the main safety feature when you pull these things to pieces, which you'll see for yourself, is it's just put somewhere you can't touch. Now, all of the stuff that we do with electricity is done in what's called circuits. Your household wiring is a circuit. Your circuit in your television, your printed circuit board, they're essentially the same thing. So to add to that list of what electricity does, there are two other components that aren't normally thought about, and those are switches and the wires. The wires themselves are tremendously important. They are a big feature of how the thing will behave. So say I've got something like this. This is fixed, really, and it's at 60 watts, so it's going to draw so many amps at 230 volts, and this wire is going to deliver that amps. It's going to power it there. If I put a wider piece of pipe, remember think about water flow, electricity flow as being like water flow through pipes, so I make this a 2000 watt lamp. That pipe's going to be really, really big, a lot of current is going to flow, and that wire is going to want to let that current flow. But what happens now is instead of this being the limiting factor, this becomes the limiting factor. So this particular wire will get hot and burn because this one is no longer limiting it. If I were just to connect these two directly, then that's called a dead short, and there is no limit to that at all because I haven't put a limit in, and the wire will burn because suddenly the wire will become the limit from the supply of where you've plugged it in the wall. So your limit that you put in needs to be enough so that this wire isn't becoming the limit. It isn't trying to deliver more than it's rated for. And if you look up wires, you'll find they have specific ratings. So somebody somewhere at some time has calculated all of this stuff and it's put down in tables. For house wiring, it's the 17th electricians regulations. Can't remember exactly the title, but it gives all of the grades of wire available and what their limits are, so you can literally look that up. And it makes sense. If you want to deliver more water, you either have to have a very big pipe or an awful lot of little pipes. And that's why you see wires as twisted. You'll see lots of thin wires all twisted around, or one thick wire. Now the same holds true for alternating current or direct current, but each one has got its own little quirks about it. Because direct current is all about resistance, alternating current is all about impedance. Impedance is very similar to resistance, but a bit harder to understand, but very similar, and at this stage that's all we're going to think about. But alternating current has a curious property, is that it doesn't travel in the centre of the wire, it travels at the edge of the wire. So it's much more common to see in alternating current supplies, like your house supply, that these wires are lots and lots of thin strands when they want to draw a lot of power. This is from a 3 kilowatt kettle, so this is stranded. In your house wiring, actually you don't draw that much, and you'll find that they're solid core wires, even though the electricity is travelling on the skin, the outer surface of the wire. How far it penetrates depends on the frequency, but it's just travelling on the outside, so here we give it lots of outsides so that it can actually cope with the limiting factor of the lamp, or in the kettle's case, of course, this heating rod. This you'll find in your kettle, it's in a coil. You'll find it in your oven, it's actually in a loop, you can see it if you look inside the oven. You found it in a household iron where it's just bent into a horseshoe shape and put onto a metal plate, and again these just plug straight into the wall. So when we're looking at electricity, you have to realise there's a couple of things about it. That is, you've got to make sure you keep to the limit or put a limiting factor in there, and that's a piece of cake. It's something like a lamp or a heat rod or a fuse, something that'll limit that draw. And then don't touch the bare wires. That's really all that it comes down to. Now we've talked about wires and switches, and when you think about what we want to do with electricity, it's only those 4 things, remember. One of the biggest things that we want to do is control it. Now control sounds like a wonderful idea, but it's really simple, it's just a switch. We need to control it because very often the place where we want to implement it and the place where we are very far apart. So a lamp, it's hanging in the ceiling and you're standing on the floor. It'd be mightily inconvenient if you had to get ladders out every night you wanted to turn the light on. So in order to control that, we have a switch. Now, switches obviously are much maligned and much misunderstood and much ignored, but they are super, super important. A computer actually is very little more than lots of little switches. That's all it is. It's a collection of lots of little switches. If you think about your television screen, your LED screen, your computer screen, your laptop screen, all they are is lots and lots of very tiny lights that are turned off and on in sequence, making your display on your computer. So lights and switches and wires are just really important components of any electronic setup. When you're doing bulk stuff, when you get a big piece of equipment, you tend not to think about it as a piece of electronics, but that's exactly what it is. And the way to protect yourself from that piece of electronics is limit it and don't touch it. Okay, I think that's probably enough about electrics and electronics and how to keep you safe from them, and what we're going to do now is do that scary, dangerous experiment.